Today we're going to be taking notes on scientific notation. In your buff binder, not your lab spiral, set up a page for Cornell Notes about scientific notation. So you should have at the top, of course, your heading and the title, Scientific Notation. And I would expect along the left-hand side, your main ideas, there'll be the scientific notation topics that we talk about and examples on the right. Why do we need scientific notation? One reason why we need scientific notation is because scientists express very small measurements and very large measurements that are difficult for most of us to comprehend when we see them. Sometimes it's difficult for us to even write them down consistently. For example, the mass of the proton in a hydrogen atom is 0.000000 and a whole bunch more zeros, 1673 kilograms. It's very difficult to write that down or even to understand what that means. Large measurements like 15 million Kelvin, which is the temperature at the center of the sun, again, also very difficult to even write down. Other numbers like the mole or other things can not even fit on a sheet of paper very easily. So with scientific notation we have two parts. The first part is called the coefficient or the significand, and that's the part that stores the numeric value. It's often called the mantissa as well. There's exactly one non-zero digit to the left of the decimal point in this part of the scientific notation. And all of the significant digits also appear here. So if the number has one significant digit, there's one number. And then if there's two or more significant digits, there's one number, a decimal point, and the other significant figures follow the decimal point. The second part is called the exponent. It's often called the power or the power of 10 as well. That part of the scientific notation indicates the magnitude or the size of the number, how big it is. An order of magnitude is the same as a power of 10. So if we speak about orders of magnitude, we're talking about within a factor of 10. The metric system is entirely set up around orders of magnitude. So a centimeter is an order of magnitude bigger than a millimeter, and a decimeter is an order of magnitude bigger than a centimeter. A meter, for instance, is 3 orders of magnitude larger than a millimeter, and a kilometer is 3 orders of magnitude larger than a meter. Now, if you have a number that is greater than 1, and you need to convert that into scientific notation, you're going to end up with a positive exponent. In this example, I have the number 1234.56, and we want to express it in scientific notation. So we start with the number, and we're going to move the decimal point to the left one place at a time until there's only one non-zero digit left to the left of the decimal point. As we do that, we're going to increase the exponent, or the power of 10, with each move of the decimal. So here we've moved the decimal one place to the left, and we've increased the power to 10 to the 1. We move it another place to the left, and now we have 10 to the 2. A third time to the left, and we're up to a power of 3. So we end up with 1.23456 times 10 to the third. And this would be our final number. Note that all of the significant figures from the original number are preserved in the scientific notation. So this number has 6 significant figures, and there are 6 here, 1 to the left and the other 5 to the right of the decimal point. If you have a number that is less than 1, and you have to express that in scientific notation, you'll end up with a negative exponent. Here in this example, we're expressing the number 0.00657 in scientific notation. We start with the number. We're going to move the decimal point to the right until there is a non-zero digit on the left of the decimal. As we do that, we're going to decrease the exponent, or the power, with each move of the decimal. So here we move the decimal place 1 to the right, and we decrease to a power of 10 to the negative 1. We move it another place to the right, and now we're at 10 to the negative 2. And we move it a third place to the right here, giving us our final number, 6.57 times 10 to the negative 3. Again, there are 3 significant figures in this number that we started with. Those 2 zeros after the decimal point are not significant, so they don't appear in the final number. The same number of significant figures appear both in the original number and in the scientific notation. So how do we multiply numbers in scientific notation? When numbers in scientific notation are multiplied, only the coefficients are multiplied. The exponents are added. So take a look at this example. We have 3.00 times 10 to the third times 2.00 times 10 to the 2. What we do here is we multiply the coefficients, the significands, the 3 and the 2, they're multiplied together. But the 2 exponents, 10 to the third and 10 to the second, we add those exponents. So this is times 10 to the 3 plus 2. These are the 2 powers that we add into the end of our number. 3 times 2 is, of course, 6, and we have our 3 significant figures, times 10 to the 3 plus 2, that's 5. So 6.00 times 10 to the 5th. Division is done in a similar fashion, but when numbers in scientific notation are divided, we divide the coefficients and we subtract the powers of 10. In this example, 8.8 times 10 to the 7 is divided by 2.2 times 10 to the third. So we're going to take the 2 significands, the 2 coefficients in the front, and divide them. 8.8 divided by 2.2. For our powers of 10, our exponents, we have 7 on top and 3 on bottom, so our power of 10 will be 7 minus 3, as shown here. So our 8.8 divided by 2.2 gives us 4, and our 7 minus 3 gives us times 10 to the 4th. This is how we do division. Remember, multiplication, we add exponents, and division, we subtract exponents. Addition and subtraction is slightly more complicated. Before numbers in scientific notation can be added or subtracted, they have to have the same exponent. In this example, 3.6 times 10 to the third is added to 5.67 times 10 to the 4th. These 2 exponents are not equal, which means we can't add them up. What we have to do is move the decimal point in one of these numbers in order to make them equal. If we move the decimal to the left, then we can increase the exponent of the number. So here we've taken 3.6 times 10 to the third, moved the decimal to the left one place to where it is now 0.36 times 10 to the 4th. Now that's not proper scientific notation, but when the powers of 10 or the exponents are the same, we can then add the first part of the number, the coefficient. So now we can add the 0.36 to the other number, the 5.67, because the powers of 10, the exponents, are equal. They're both, in this case, times 10 to the 4th power. We go on and add these together like this. We have 0.36 plus 5.67, and the powers are the same. In addition, we don't do anything with the powers. 10 to the 4th stays 10 to the 4th. We end up with 6.03 times 10 to the 4th. If we'd ended up with a number that was greater than 10, or greater than 9.99, let's say, if there were 2 digits to the left of the decimal place, we would have had to move the decimal over in order to make it have only 1 digit to the left of the decimal, and then we would have had to adjust our power of 10, or our exponent, the same way. So if we moved our decimal point over by 1 to the left, we would have increased our exponent by 1. If this number was 11.03 times 10 to the 4th, we would have changed it to 1.103 times 10 to the 5th. Now this example was for addition. Subtraction is done the same way. You can subtract the first part of the number, the coefficients, only after you've made the exponents equal. Once they're equal, you just subtract the same way as you would as we just added, and keep the exponents the same unless the number ends up being above or below above 10 or below 1, in which case you have to adjust the exponent. And that's all we have.